Say this is exercise 25.14, and in it they give you a copper wire. It says it has a square cross-sectional area with the side length of 2.5 millimeters. It gives you the length of that wire, which is 4.3 meters. The current it is carrying, 3.3 amperes, and the density of free electrons, which that's usually N and called the concentration, that's 8.5 times 10 to the 28th meters to the negative third. It wants the magnitude of the current density, the magnitude of the electric field, and then how much time you need to travel the length of the wire. So I already have it written out. So let's see. So here's what we have. We have a square cross-sectional area with 2.5 millimeter length sides, and that is, we want that in meters. So 2.5 times 10 to the negative third meters. We have our length, our current, and then we have N. This is our concentration, and they called it the density of free electrons. So that's the same thing in your equations as just N right here, the 8.5 times 10 to the 28th. In A, it wants the magnitude of the current density in the wire. So J is current density. So we have this equation right here, current over area. Area in this case is a square cross-sectional area. So for a square, you have the side length squared, 2.5 times 10 to the negative third for meters squared. You just go ahead and plug that into your equation over here, 3.3 over 2.5 times 10 to the negative third squared into a calculator, and you get 5.28 times 10 to the negative fifth, and the units for that are ampere over meter squared, and that is the current density. For B, it's wanting the magnitude of the electric field in the wire. So electric field is probably one that you're more familiar with, and that's PJ. P in this case is resistivity. Resistivity changes with material. So resistivity of copper is 1.72 times 10 to the negative eighth ohm meters. These are values that you're probably just going to have to look up in a textbook, in a table, or Google is the easiest. So now that you have that resistivity, this part's really simple, and you already have J from the last part. So you go ahead and just multiply those, and you get 9.08 times 10 to the negative third volts over meters. Third part wants to know how long it takes to travel the length of the wire. So this is our new equation that we're going to use, where T is time, L is length of wire, N is the concentration, the density of free electrons that it gives you there, Q is a charge, and J is the density we found in the first part. So Q, we're talking about electrons, so we're using the charge of electrons, the absolute value of 1.6 times 10 to the negative 19th. We plug in all of our values, 4.3 meters, 8.5 times 10 to the 28th, times 1.6 times 10 to the negative 19th, and divided by the J we found, 5.28 times 10 to the 5th, and we get a simple 1.1 times 10 to the 5th seconds, and that is your answer for C.